Hello, viewers. Good evening to everyone. I want to welcome every one of you, especially to this semester's edition of facilitation for CHM416. Today is the first day. My name is Professor Olayinka Jani. I am your facilitator for this section. So always check the information on the virtual learning environment. This going to be 8 weeks of facilitation. We believe that it's going to be very, very exciting, and it's going to be a good platform for learning and for interactions. Thank you again as we come up on board for this first facilitation class. The facilitation we are starting today. All the facilitations have been grouped into 8 weeks. Every content of the course material has been put in that form and that perspective for easy access to each of the contents to learn per time. So CHM416 is going to be coming up every Tuesday like this for 1 hour between 6 and 7. But it's advisable that a few minutes to 6, the learner should begin to join the platform through the Zoom link that I have already sent to your virtual learning environments. And I've also sent that Zoom link even onto your email through the module email and through the normal email method. So all you need to do is every Tuesday, few minutes to 6, just go to that link and click it to take you to the Zoom page of this course so we can do justice to it. Then another thing you need to know is that facilitation is not like a physical class, and yet you are not deprived of every privileges and opportunities that people that have physical contact gain in learning, because it's an environment where we can also interact to ask ourselves questions, to contribute. And as part of my teaching philosophy, I believe that teaching should be student-centered, and students should be the drivers at the seat of the cars of their learning, to learn at their own comfortable pace, to learn with their own level of flexibility, and to learn with their own nature of adaptation. And by this, you find learning interesting, and then you find students being in charge of their learning space. So it's on that note, I would like to tell us that the expectation is that before every week of facilitation, I will have sent to you on the virtual course page, 1, the instructional material that is to be read before the class. 2, the instructional video to watch before the class. When you have done due diligence to these 2 before the live facilitation of 1 hour, after having watched those videos and having read those material, there may be some area there that you are not very clear. Those areas are those areas you need to pinpoint out. So when we come for the 1 hour of live class, then it will be easier for you to ask that question. Then we can deliberate upon it among ourselves to see how to solve that questions. So learning should also be problem-based, so that we are able to provide solution at every point in time. And at the same time, so that learning is not just that is of the head, but learning should contain both the head knowledge and the hands-on, that you are able to use your hand to deliver that which you have learned. And these are part of the opportunities and privileges that the learner will enjoy on this platform. Let's make sure we come down on time to join the class, so that when we say 6 to 7 is 1 hour on live facilitation, we are able to use it judiciously throughout the course. Once again, thank you and welcome on board. CHM416 is organic synthesis by title, and it's a 2-unit course. In the module 1, it is made up of 4 units. The unit 1 is oxidation reaction. Unit 2 is transformation of alkenes to epoxide, diols, and carbonate. Unit 3 is transformation of alcohol to carbonate compounds. And the unit 4 is transformation of arynes, which are the benzene family. But I've told you that we have sectionalized this into 8 topics so that it can be covered in 8 weeks of our facilitation. For example, today, which is week 1, topic 1, we are going to be looking at topic 1 being made up of 2 units. That is unit 1 and unit 2. So at the end of these units, 1 and 2, the learner should be able to, number 1, define oxidation reaction. Number 2, recognize oxidation in organic reaction context. Number 3, the learner should be able to list some oxidizing reagents that can be used. 4, you should be able to discuss the conversion of alkene to epoxide using the right oxidizing agents or reagents. And lastly, the student or the learner should be able to describe the functional groups transformation via oxidation processes. Now, because I've not seen anyone indicating interest of any area that wants us to zoom in on, and being the first week, the first class of facilitation, I will try to run through this course material for this topic 1. Then when you watch the video, if you have any challenges, then you can bring that on board so that we can look at it next week. Or if you cannot wait till next week, of course, you can send me a mail concerning what are the area of the challenges, then I will respond to such mail accordingly. So what is oxidation? Oxidation are various contents and contextual definition depending on various areas where they have been relevant. Oxidation, of course, in inorganic chemistry is usually considered as a loss of electron. This is because it results in high charge. For example, if ion 2 plus is going to ion 3 plus, what has happened is that ion 2 plus has lost 1 electron for it to become ion 3 plus. This is an oxidation. However, oxidation in organic molecule, which is the basis for organic synthesis, is therefore defined as either the removal of hydrogen or the replacement of hydrogen atom attached to a carbon with another more electronegative elements. Most frequently used, more electronegative elements are the oxygen and the halogen. How do we illustrate oxidation? Having known the oxidation definition in organic molecule, oxidation in organic molecule can be illustrated in 2 different ways. The first one, we are talking about the successive oxidative dehydrogenation of ethane as a first illustrative example. The second example is the oxidative series of transformation that occurs in methane. Let's look at the first one. The first example of the illustration is successive dehydrogenation of ethane. Remember, we have said oxidation simply means the removal of hydrogen or the addition of electronegative elements like oxygen, or the replacements of the hydrogen with electronegative elements. So when you are looking at this in terms of the dehydrogenation of ethane, it means you are removing hydrogen from ethane gradually. If that is the case, then that is oxidation. So the loss of the CH bond to form a new CC bond in a successive dehydrogenation, that means the removal of hydrogen of ethane in order to get ethylene, is example of oxidation process. You can see here from this place, you can see here from this place that ethane is C2H6. When a pair of hydrogen is removed from two adjacent carbon, it contributes additional bond to the middle, and therefore the 6 hydrogen has become 4 hydrogen as you find it in ethane. And therefore the double bond, the single bond of carbon-carbon has become double bond carbon-carbon. So going from ethane to single bond to ethane double bond, a level of oxidation has occurred. How? By removal of 2 hydrogen. Now, it is also possible that 2 hydrogen can be removed from adjacent carbon atom to form a triple bond between them. When this happens, 4 hydrogen in ethane has now turned to 2 hydrogen in ethane. So from ethane to ethane, there are some level of oxidation that has happened also, because there is a dehydrogenation, or there is a removal of 2 more hydrogen. So when we look at the journey of this illustration from ethane single bond into ethane double bond, and finally into ethane triple bond, we can summarily say that ethane is the most reduced. And as you are removing the hydrogen, oxidation is going on. So ethane is the most oxidized. So that's a successive dehydrogenation as an example of a definition of oxidation. And that has to do with gradual removal of hydrogen from ethane to get ethane double bond, and from ethane to get ethane triple bond. So let's look at the second example of definition of oxidation, and that is oxidative transformation of methane. If you look at oxidative transformation of methane, the degree of oxidation actually increases as, number one, as more hydrogen atoms are removed, oxidation is increasing, just as we have said before. Number two, as more oxygen atoms are being added, oxidation is increasing. And number three, as more multiple bonds are formed, oxidation is increasing. If you can look at the first ethane that we talked about, the first one, which is ethane, has single bond. And when the oxidation takes place, we have ethane where there is double bond. And when ethane more oxidized by removal of hydrogen, we have ethane, which is triple bond. So the higher the increase in the multiple bond character, the higher the oxidation process. That's what we are saying. And the more you are removing hydrogen from a system, the more you are increasing the oxidation. And the more you are adding oxygen to a system, the more you are increasing. So when we look at methane, for example, is CH4. Methane is CH4. And then if you look at it, it means one carbon surrounded by 4 hydrogen. Immediately one oxygen is inserted into the side of that one of the hydrogen, you have methanol, which is CH4 with 1 oxygen. Remember, the second definition says addition of oxygen is oxidation. So even though there are still 4 hydrogen in methanol, just as in methane, but for the fact that now high oxygen has come in methane, and there was no oxygen in methanol, and there was no oxygen in methane, it shows that methanol is a more oxidized compound than methane. So oxidation is increasing. Then from methanol to methanol. If you look at methanol now, two things in that three condition up is fulfilled. You see, the methanol has only one oxygen, and methanol also have one oxygen. So we cannot distinguish the oxidation using oxygen addition because it has the same number of oxygen. However, methanol has 4 hydrogen, but methanol has only 2 hydrogen. So going from methanol to methanol means there is removal of hydrogen, which is the first one. So that's oxidation. Secondly, methanol has 4 single bonds around the carbon atom, but methanol has a multiple bond, which is a double bond between carbon and oxygen. That was fulfilling the oxidation by this third condition, which says the more multiple bonds are formed, the more oxidation is increasing. So methanol has single bond, methanol had a double bond. So increase in multiple bond character in methanol makes methanol to be more oxidized than methanol. Now, when we look at methanol going to methanoic acid, I said it's another oxidation. In that case now, we know that the number of hydrogen has not increased because methanol has 2 hydrogen and methanoic acid has 2 hydrogen. So you cannot distinguish the oxidation by total number of hydrogen. But if you look at methanol, it has only 1 oxygen. Or if you want to use the double bond character, it has a double bond in methanol and there's a double bond in methanoic acid. So you can't use multiple bond character, which is the third evidence in such. But you can use the second evidence in such, in that methanol has only 1 oxygen, but methanoic acid has 1 plus 1, which is 2 oxygen. So addition of more oxygen from methanol to methanoic acid makes that to be an oxidizing process. Now going from methanoic acid to carbon dioxide. If you look at methanoic acid, there are 2 oxygen, 1 and 2. If you look at carbon dioxide, there are 2 oxygen, 1 and 2. So you cannot use this middle definition to know whether oxidation has taken place when you move from methanoic acid to carbon dioxide. So let's look at another thing. Another thing is that there is multiple bond character here in methanoic acid, but only 1 double bond. But carbon dioxide has 2 double bonds. So the third condition can be used to say, yes, there's more oxidation that has taken place. Then, if we look at the number of hydrogen, methanoic acid has 2 hydrogen atoms. Carbon dioxide has lost those 2 hydrogens. So condition 1 and condition 3 has fulfilled to us that carbon dioxide is more oxidized than methanoic acid. So in a summary, methane transferring and transforming to methanol, and from methanol to methanol, and from methanol to methanoic acid, and from methanoic acid to carbon dioxide are all increasing oxidation processes. So in a summary, we can say in this second illustration that methane is the most reduced species here, while the carbon dioxide is the most oxidized species, even though all of them have 1 carbon each. But the nature of the double bonds or the multiple bond character around the carbon, the total number of oxygen around the carbon, the total number of hydrogen that has been removed from the system are all contributory to measuring the degree of oxidation. Based on what we have just learned, let's look at class activity 1. There are 3 brief questions there. Number 1, based on organic chemistry, what is oxidation? Of course, if you remember carefully when we started using ion 2 going to ion 3 as an example of defining oxidation in inorganic chemistry, which has to do with the loss of electron. But when we were talking about the definition in organic chemistry context, we said it simply means the addition of the removal of hydrogen, which is called dehydrogenation, or the addition of a more electronegative element or atom, which is in most cases oxygen. So Oxidation as regard carbon organic chemistry can be defined as the addition of oxygen as an electronegative element to replace the hydrogen or the removal of hydrogen as an electropositive element. Number two, arrange the following functional groups in the order of increasing oxidative states: carbon dioxide, methanol, methane, and methanol. We know that carbon dioxide, of course, if you want to answer this question successfully and correctly, you must first of all get to know the molecular states. Carbon dioxide is having 2 oxygen, even though it has only 1 carbon. Methanol is having 1 oxygen, 4 hydrogen, even though it has only 1 carbon. Number 3, methane is having 4 hydrogen alone, joining with even that 1 carbon. And methanol is having 2 hydrogen, joining with the carbon, 1 carbon that now have oxygen. So if you look at all these things, carbon is not what determines this, because carbon have the same 1 carbon atom throughout. But when you look at this, if we are to arrange this one in the order of increasing oxidation, the most reduced form of it is the one where carbon has 4 hydrogens. So this one will be the first one, is the least reduced. And what will follow it is that, oh, there's another carbon that has 4 hydrogen here. But in that 4 hydrogen, of course, it's having the same number of hydrogen as the first one. But the reason why it's more oxidized is that in addition to its 4 hydrogen, there's addition of an oxygen. So this will be the number 2. Then when we come to the other remaining 2, carbon dioxide to have addition of 2 oxygen, methanol has addition of only 1 oxygen. Carbon dioxide have no hydrogen at all anymore. Methanol has 2 hydrogen. Therefore, methanol is less oxidized than the carbon dioxide. So carbon dioxide is in. So this is how to arrange all this according to the property we have used. Number 3, the most reduced form among the 3 hydrocarbon, which are ethane, double bond, ethane, single bond, and ethyl, triple bond, is what? If we look at this carefully, we said the most reduced must be the one that begin to lose its hydrogen, to begin to get oxidation, to go to the most oxidized. So when you look at ethane that have 1 carbon and 4 hydrogen, ethane has 2 carbon and 4 hydrogen. Ethane has 2 carbon and 6 hydrogen, and ethane has 2 carbon and 2 hydrogen. So when we look at this, we discover that C2H4 is ethane, because there's a double bond there. C2H6 is ethane, because they are all single bond throughout. And C2H2 is ethane, because it has a triple bond. So when we look at this, the one that have the highest number of hydrogen will be the most reduced. And as you are now taking those hydrogen away, you are getting it oxidized, until you get to the most oxidized. So in that case, the most reduced is C2H6, because even though they all have 2 carbon, it has the highest number of hydrogen, which water down oxidation and increases the reduction. Because reduction means addition of more hydrogen, while oxidation means the removal of such hydrogen. So when we look at it, which of this is the most reduced? The most reduced is C2H6, which is ethane. If we are asked which one of them is the most oxidized, the most oxidized is one that have lost almost all of its hydrogen. So C2H4 lost only 2 hydrogen, C2H2 lost 4 hydrogen. So the most oxidized is C2H2. While the most reduced is C2H6. So the middleman there will be C2H4. And that takes us to the second unit, as you have told us earlier, that this topic 1 is combined under the first and the second units in order to make sure that our facilitation covers all of course contents and the materials within that 8 weeks of facilitation. So oxidation, oxidizing agents. You can call it also oxidizing agent or oxidizing reagent. It is an agent because it's a reagent. So we can use these two interchangeably. We are referring to the same thing. So when we are talking about oxidation as a process, it will take the presence of oxidizing agent for oxidation to take place. So all these things we are talking about, methane going to methanol, methanol going to methanol, methanol going to methanoic acid, and methanoic acid going to carbon dioxide. They are all synthetic transformation from one form to another, either by increasing the number of oxygen or by reducing the number of hydrogen. But this thing cannot just be in the reaction vessel and begin to change on its own. It takes a game changer to change the tone of the game. It takes a world changer to give and provide quality leadership that can move the world forward. So in the same vein, when we say there's oxidation is taking place, either partial oxidation or total oxidation, it will take the presence of an agent to effect that. So the agent that will effect oxidation at any strata are called oxidizing agents. An oxidizing agent, if you get to know them carefully in the redox reaction, if something is an oxidizing agent, is because he itself is going to be reduced. Because as an oxidizing agent, is oxidizing something from one form to another. And for him to have oxidized something, then himself may be reduced. So several examples of oxidizing agents exist, especially in the 21st century, where organic synthesis has been the most important, one of the most important area of specialization in drug design and drug synthesis. So some of the common oxidizing agents, we are going to be listing them here as a key player to knock off a particular compound and transform it to something else. If you see the images here, you see some of those big fellas, they are the oxidizing agent. And you can see that thing that is down on the floor, they wrote arcane. It means by the influence of these game shakers that you looked at, there can be the loss of identity of arcane in order to form something else. That's why we are saying some of those reagents that we're going to be looking at have majorly 5 of them. The first one is chromic acid. The second one is pyridinium chlorochromate, PCC. The third one is potassium permanganate. The fourth one is osmium tetroxide. And the fifth one is called per acid. Per acid is also known as peroxyl acid because it's just like a carboxylic acid that now have one more extra oxygen. That's why we call it peroxyl acid. So it is important for us to now begin to look at how do we prepare each of these oxidizing agents before they can do the work of transformation of one group to another. So by reacting, let's start with chromic acid. How do we prepare chromic acid? By reacting sodium or potassium dichromate with sulfuric acid, you can prepare chromic acid. As you can see in this equation, the dichromate ions that was dissociated from that potassium or sodium dichromate is acted upon by sulfuric acid, and it leads to an oxidation to give chromium increasing oxidation state to form dihydrogen chromic, and then when you add water to that, it forms 2 molecules of chromic acid. And when you look at this, underneath it's showing the structural identification of how such are written. If you look at this chromium, dichromium heptaoxide, which is the same thing as chromate ion, The structure is saying that there are 2 negative ions, there are 2 chromium, and there are 7 oxygen. So the structural representation of that is what we see down here. And the first minus is here, the second minus is here. So if we are looking at it as potassium dichromate, it means there is a potassium plus here that's attracted the O negative, and there's a potassium plus here that attracted the O negative. So the ionic form of the equation is what you see here. The molecular form is here, but when I remove this potassium, then this is the ionic form of the dichromate. And this ionic form of dichromate, when being treated with acid, sulfuric acid, as shown here, we discover something, and that is that there is a hydrogenation of that. So there is a replacement. So potassium willingly leave that place for hydrogen to come in. Hydrogen cannot displace potassium in the periodicity. But what we are saying is that the potassium has seen some other anion, so is willing to go and form a stronger ionic bond. And when it has gone, then the hydrogen from sulfuric acid, which is proton H+, can be easily attracted by the anion oxygen to form 2 hydrogen coming in. And that's what we are saying. This molecular intermediate, the structural feature of that molecule is what we see here, where 2 hydrogen has now come in to counterbalance the 2 negative charge. And that's why we have this. So upon treating this with water, we discovered that there is a breakage. There is a breakage, and when there is a breakage, it means that there is a repetition of this thing in 2 different forms. So it begins to give us a 2 molecule. 2 molecule. How does that happen? If there's a cleavage here, this with the negative oxygen pick 1 H+ to form this first compound. And that H+ comes from H2O, right? It comes from H2O. So when you look at H2O, mechanistically, when this one broke up, the negative oxygen attract this hydrogen to form OH. Why this one becomes a negative charge on oxygen? So the OH that you have had, we have a nucleophilic attack to donate to this place. So you end up getting 2 molecules of this chromic acid. Having known the synthesis or preparation of chromic acid, what is the major application of this oxidizing agent? Chromic acid is very valuable in the oxidation of primary alcohol to carboxylic acid. Primary alcohol, of course, we go through a series of transformation. The primary alcohol gives rise to, upon oxidation, gives rise to aldehydes. And aldehyde does not stop there. It uncontrollably transforms and oxidize to carboxylic acid. So when you are dealing with primary alcohol, the best way to turn salt to carboxylic acid is to use the chromium or the chromic acid. You can see this is a primary alcohol. An alcohol, of course, is a compound that have hydroxide linked to aliphatic carbon. And when you say something is primary alcohol, it means the carbonyl carbon, which is the carbon that hydroxide is linked to not is linked to at least 2 or 3 other hydrogen. You can see the first hydrogen here, the second hydrogen here. So this is a primary alcohol. But if the carbonyl is linked to, so you can see that it's linked to no more than 1 other carbon. But if it's linked to about 2 other carbon, by reducing this hydrogen to be only 1, then you have secondary. And if it's linked to 3, by removing these two carbon, then two hydrogen, then it becomes the tertiary. So you must be able to know the difference between primary, secondary, and tertiary alcohol. So, like for example, if I have this OH, it's on a carbon, and you know each carbon is tetravalent. So if carbon has taken one bond with OH, it needs 3 more. If this 3 more is taken, it's filled with hydrogen all the way. That is a primary alcohol. If it is also linked to 2 hydrogen and no more than 1 more other carbon, it's a primary alcohol. However, if that carbon that is linked to OH is linked to 2 other carbon, 1, 2, this place is now hydrogen. That's the secondary alcohol. However, if the carbon that carry the OH, which is carbonyl carbon, has all of its 3 other bonds directly linked to him, linked to carbon atom, then this is what is called a tertiary alcohol. So a primary alcohol can easily be treated with chromic acid using acidified potassium dichromate, which is to generate chromic acid. You see the intermediate is a aldehyde, C-double-OH, which cannot stably stay, but in the presence of the aqueous medium transform to something which lead to carboxylic acid. So the application of chromic acid is good in the treatment of primary alcohol to get carboxylic acid. It's also good in the treatment of secondary alcohol to get ketone. If you look at this carbonyl, the hydroxy group is on this carbon. If you look at this carbon that is carrying the hydroxy group, check all other 3 bonds that comes into it. This one that comes into it from down is linked to hydrogen. This one that comes to it from up is linked to carbon. This one that comes into it from benzene is linked to carbon. So you can see this carbonyl is linked to 2 other carbon, 1 and 2. So this is a secondary alcohol. Treating with chromic acid, which is freshly prepared from acidified potassium dichromate, turn this one to a ketonic group. So these are 2 very crucial applications of chromic acid in oxidation process. That leads us to the second oxidizing agent, and that agent is pyridinium fluorochromate. From the word, from that same word for that name, it shows us something, that this component or this compound is made up of 3 components. You have pyridine, you have the chlorine releasing agent, and you have the chromate group. And that gives us the simple definition and the equation of reaction. So pyridinium fluorochromate is otherwise known as, in acronym form, PCC. So PCC is prepared by the reaction of pyridine with chromium trioxide. That's where the chromate is coming from. And conc HCl, that's where chlorine is coming from. So the equation of reaction is saying this is pyridine reacting with HCl, reacting with chromium trioxide, it will form a complex. This is pyridine. Pyridine is a 6-membered ring like benzene, in which one of the carbon of that benzene has been replaced with a nitrogen. This is pyridine. So pyridine reacting with chromium trioxide, we get pyridine chromate. There's an addition reaction, which is excessive methylation has happened there to make that nitrogen to be ammonium centered. Therefore, but for this positively charged nitrogen, it is counterbalanced by an anion of chloride. So this is the molecular representation of PCC. Pyridinium, because of the positive center, chloro, because of this negative charge that balance that, and chromate, because of chromium trioxide. This complex is what is represented here by this structure. So PCC, what is the major use of PCC? PCC is used for selective oxidation of primary alcohol. Remember we said oxidation of primary alcohol will go to aldehyde, and you can't stop that reaction to isolate that aldehyde, because in the presence of water and air, it quickly converts itself to carboxylic acid. But if your intention is to get an aldehyde, not the carboxylic acid, so you won't use chromic acid, but you will need something that can selectively oxidize it partially to the aldehyde and stop it there. And that thing is no other but pyridinium chlorochromate. Sorry, you have to correct this circle. It's PCC, not PPC. It's PCC, just like this. Pyridinium chlorochromate. So if we are giving things like this now, for example, if you remember this structure, when we used chromic acid in the previous page, it led this one to because it's a primary alcohol, it led it to carboxylic acid. But now we want it to stop at that aldehyde, not going to the carboxylic acid. You have to change the oxidation agent from the chromic acid to PCC. And PCC work well in a solvent called dichloromethane most of the time. You can see selective reduction of primary alcohol to aldehyde. We take PCC as the oxidizing agent. Potassium permanganate is another oxidizing agent. How do we prepare potassium permanganate? Potassium permanganate, it's very important for us to know that it can work both in acidic and in alkaline medium. When you are using it in the presence of acid, we call it acidified potassium permanganate. It will oxidize things and it will give you a particular set of products because it's an acid medium. However, it can also work in alkaline medium. We call it alkaline potassium permanganate. That will also give another product. So how do we prepare a solution of potassium permanganate? You carefully weigh about 3.3 grams of potassium permanganate salt and dissolve it in 1 liter of deionized water, each on a steam bath gently for 2 hours. Having done that, allow the solution to stand for 24 hours. Then you see some settlements, filter carefully the clear solution. Then that solution is ready to go and be used as the potassium permanganate oxidizing agent. What is the application of potassium permanganate? Both potassium permanganate and osmium tetroxide in aqueous base are used to convert alkane to diol through a same addition. What do I mean by this? Let's look at what we are trying to say here. If you have, for example, we have C-1, let's say like this. If you are treating this with potassium permanganate in alkaline medium, you know alkaline medium means in the base, in a strong base environment. You can treat it in the presence of potassium hydroxide or sodium hydroxide. When you do that, the oxidation that will happen here will mean the addition of hydroxyl across the 2 carbon unsaturation But that oxide, hydroxide, will actually attack that carbon-carbon bond from the same side. That is what is called a syn addition. So if this one will be a syn addition, it means that the space for the carbon will be attacked from the same side. If the hydrogen has given way up, then the OH will attack from base. The OH of the second one will also attack from base. And when this happens, the double bond becomes single bond. So you can see that there is addition of two hydroxyl group to turn the double bond of alkene to single bond of a diol. That was why when you see the picture of the other time, when you saw those fellas that were standing, potassium permanganate is one of them. And when you saw the one that was down on the floor, is alkene. So alkene can be completely turned its identity from where it is and be down to get something else by the influence of oxidizing agent potassium permanganate. So this is a diol. A 1,2 diol means two carbon atoms in position 1 and 2 to each other now have hydroxyl coming to them. The same way the alkaline potassium permanganate will turn an alkene to a diol is the same thing that osmium tetroxide will do. But one thing you have to note is that the stoichiometric and the stereospecific addition, it will not add up to go and add the hydroxy on this one below and go and add the hydroxy of this one above. No, it will add it from the same side. That's what we call syn addition. If it is not adding from the same side, let's say, for example, oh, you have the hydroxy OH of this is adding from below, and the hydroxy of this one is adding from above. They will also be diol. But in this diol now, it's not on the same side of this carbon-carbon that both added. One added below it, one added above it. That is what is called anti-addition. Anti-addition cannot take place if you are using potassium permanganate or osmium tetroxide. The addition across the double bond to form single bond will form a diol that is a syn addition. That's the meaning of syn addition. But what is now the major disparity between potassium permanganate and osmium tetroxide? If they are going to give us the same syn diol, notice here, the osmium tetroxide will give a better yield of your diol products. It will produce your diol at a higher yield. However, because of that, it's toxic. The toxicity of it makes it to be not friendly in human use. So even though osmium tetroxide will give you a better yield of diol, potassium permanganate is safer to use, even though it will give you lower yield of the product. So you have to count your costs and then make up your mind which of these is much important for you to get more of your product, which is atom economical, or to use it while your life is in safety. So that's why most of the time in the organic chemistry, you don't hear talking much about osmium tetroxide, but you hear every time and every day, even in the undergraduate laboratory, you hear talking about potassium permanganate because it's environmentally friendly and it's safe to use. But osmium tetroxide will give you a better yield, but it is toxic. So you avoid toxicity so that your life is safe to make your contribution to the body of knowledge. So you can see the osmium tetroxide that we just explained before. You can see how it works on the double bond. You can see the osmium tetroxide, we add hydroxyl across that carbon-carbon double bond and turn it to carbon-carbon single bond and a diol. But we are saying that there's an intermediate that will be formed first before it's rearranged to a stable product. And that's what we are saying, that osmium we use is 2 oxygen to actually coordinate on your carbon. to form an ester 5-membered system, which is called cyclic osmate ester. This cyclic osmate ester, because the osmium tetroxide has added the two oxygen from the same side of the plane of your carbon-carbon bond. You can see now by the time the osmium will break away, the real OH will be on the same side. You can see the OH here is adding from up, OH here is adding from up. So this is a diol, truly, but it's a diol that is formed by a same addition because the two oxygen added to the same side of the double bond. The same thing with the permanganate, the same side which is up here in this place. And when it rearranges, you see the two OH up. Not that OH is here for the first one, and OH is now up for the second one. That is not syn addition, that is anti-addition. So if your product of interest is to get a diol that is an anti-addition, then osmium tetroxide and potassium permanganate will not be a very suitable oxidizing agent. So knowing oxidizing agents, the capacity of what they can do, and the required product that you are looking for actually will enhance your skill of to know when do I use this and when do I use that. Now, knowing their profile in terms of toxicity and the efficiency in terms of the product yield also can give you a lot of understanding towards this. Another oxidizing agent is ozone. Ozone are 3 atoms of oxygen. What is an ozone? It's a highly reactive allotrope of oxygen. It's actually generated or prepared. When you're talking about preparation of ozone actually is a natural phenomenon, but scientific understanding has also shown that there are some kind of processes in the laboratories or in the electrical unit that can also lead to the discharge of ozone. So it is generated actually by passing a stream of oxygen over a high voltage electric discharge. It is possible to actually smell ozone in the atmosphere. After a lightning strikes or after a lightning storms, if the lightning has struck nearby, you will smell ozone because ozone is abundant in the atmosphere and can be released through that lightning discharge. Application of ozone in ozonolysis. It involves direct addition of 3 oxygen across a double bond of alkene to give an unstable intermediate, which rearranges to a stable intermediate called ozone, called ozonide. The first thing it returns to is the intermediate that is not stable. You see, for example, if you look at this carbon-carbon double bond, and you are treating with ozone in presence of dichloromethane, you discover that the 3 oxygen of the ozone will form a ring, a crown ring head on top of those 2 carbon to form a new 5-membered ring. At that time, you are having a molozonide. What we call molozonide. A molozonide is not stable, intermediate. It will rearrange itself quickly by doing what? By establishing 2 oxygen up and getting the 1 oxygen down, in this format. You see your carbon here, you see your carbon here. Out of the 3 oxygen, 2 forms the closing cage up and 1 forms the closing cage down. It's a more stable intermediate, which is called ozonide. So you must know the difference between molozonide and ozonide. So this ozonide, when you form it, the process of converting alkene, the addition of ozone to get this, is called ozonization. And that ozonization is giving you the ozonide. If you treat the ozonide by hydrolysis using zinc dust in acetic acid, then what will happen is that it will break into 2 mixture of carbonate. And this is how the breakage will go. You break it here, the oxygen here goes with this carbon to form these products. The oxygen here goes with this carbon that have R2 to form this aldehyde or ketone that have R2. Then the last oxygen here goes together with the zinc acetic acid mixture to get out of the system. But if you want to also look how the single bond becomes a double bond, even in that perspective, you discover that it's easier because when you come in here, you can do it homolytically or heterolytically, it will both give you. If you do it heterolytically, the whole double bond between carbon, oxygen breaks away to form a double bond here. And when that happens, this breaks out of this to form a double bond here. And that happens to give this O negative charge away. And that's why this one now becomes a double bond oxygen to carbon R2, which is this one, and a double bond oxygen to carbon R1, which is this. So the whole content of this is saying oxonization plus hydrolysis is what we combine to form what we call oxonolysis. So the oxonized intermediate is hydrolyzed with zinc metal in acetic acid to yield the mixture of carbonate, which could be mixture of aldehyde and ketone. It could be mixture of aldehyde and aldehyde. It could be mixture of ketone and ketone, depending on the nature of R group that is attached to your carbon double bond. So it's easier for us to say oxonolysis simply means the addition of ozone to a carbon-carbon double bond of alkene, followed by the hydrolysis with zinc in acetic acid to form mixture of carbonyl compound. So we are talking about oxonolysis. You can break it into two. The ozone is coming from the ozonization part. Then the hydrolysis is where the lysis is coming from. So when you join oxonization plus hydrolysis, you get oxonolysis. So oxonolysis is very good for us to know the position of double bond. If they give you a pentane, you don't know whether the position of double bond is between carbon 1 and 2 as pent 1 or whether it's between carbon 2 and 3 as pent 2 But when you do oxonolysis of such, the two carbonyl compounds you get, face them together at their carbonyl part and remove the oxygen that you introduce. It will lead you to the right starting material of that alkane, whether it's pent 1 or pent 2. This is one of the crucial applications of oxonolysis in structural utilization of natural products. So if you want to go back, assuming you don't know this starting material, assuming you don't know the starting material here, and you want to know it, all you need to do is that after the oxonolysis, just write your final product in such a way that your oxygen is facing each other. You remember that this is double bonded carbon-carbon, there's no oxygen there. So if the oxygen has come in there, it's because oxidation has taken place. So if you want to know what is the alkene starting material that I don't know before, all you need to do is that once you know the structure of your carbonyl product, write them in such a way that they are facing each other in the position of oxygen you have introduced. This is R1. The second product here is the one that have oxygen linked to R2. I'm redrawing it because the way it is drawn here, they are not facing each other. And I want to show you a very convenient way to establish the unknown structure of an alkene having gone through oxonolysis as a structural utilization procedure. You can see these two products that was produced from this starting material is now facing each other here. What we are saying is that having done this, to know your alkene is easy. Just take away this oxygen, and then whatever is remaining there, just join them together straight. Immediately you do that, you will look at this is alkene, is no longer different from your starting material. So you are able to know the position of your double bond in the starting material if you are able to know the aldehydes and ketone mixture, or the mixture of carbonate that is formed, you can turn it back and know what was the alkene starting material. Another one is peroxide acid or par acid. How do we form par acid? Par acid is formed by reacting acid itself, which is organic or carboxylic acid, with hydrogen peroxide. 30% of hydrogen peroxide is sufficient enough. When you are treating that, one more oxygen will be infused into your carboxylic acid functional part. And that one oxygen is what makes it to be very strongly reactive. You can see example of acetic acid having a COOH being treated with peroxide here. Water will break away, as you can see, and the remaining one more oxygen will be fused into your acetic acid. You can now have, before it's 1 and 2 oxygen, but now you are now having 1, 2, and 3 oxygen. So this second oxygen that is fused in is what turns acetic acid to per-acetic acid. It's a very strong oxidizing agent that when you use it to oxidize something, this extra oxygen that has entered in will be released to the other group to oxidize them. You remember that oxidation in organic is addition of oxygen. So the excess oxygen here was fused in this guy so that when you take him to the next place to react with something, he can now release this oxygen to oxidize that thing. That's per-acetic acid. We have per-benzoic acid. It's known per-benzoic acid can be prepared by treating benzoic acid with hydrogen peroxide. Trifluoroacetic acid can be done. Treating trifluoroacetic acid with hydrogen peroxide, then you have per-trifluoroacetic acid. Per will always be there, per after that, because you see, this is no longer COOH. This is no longer CO2H, it's CO3H. So this is the thing that we use in Bayer's vinegar oxidation agent that can make you to forcefully oxidize ketone further. That's at higher level. You know, in the 100 level, they will tell you primary alcohol is oxidized to aldehyde and from there to carboxylic acid. And they will tell you secondary alcohol can be oxidized to ketone and it will stop there, no further reaction. But in advanced state, you are at 400 level. It is interesting for you to know that with per-acetic acid or per-acid, you can forcefully oxidize a ketone further. So, what are the applications of per-acid? A, oxidation of alkene. So, per-acid can oxidize alkene to give rise to epoxide. Epoxide are cyclic ether, which are also known as oxirane. We can also use it to transform alkene to trans-1,2-diol. You remember that when osmium tetroxide and permanganate were being used, we said that no, they can only give a syn addition. A syn addition means that the hydroxyl group will come on the same side. However, if you are using per-acid will do the other way, which is like anti-addition. Per-acid will make hydroxyl to come below in one carbon and you come above in the other carbon. And by that, automatically, you have a trans product being formed. So if your aim is to get from an alkene a diol that is a trans product or that is formed as a result of anti-addition, then you will not need to use osmium tetroxide or potassium permanganate, but you will need to use peroxyl acid. The second thing is that oxidation of ketone, which earlier in the 100 level they say is not possible, with per-acetic acid or with peroxyl acid, then oxidation of ketone can be effected to produce ester, if it is a straight chain compound, or to produce lactone, if it is a cyclic compound, because cyclic ester are also known as lactone. So the A above in the formation of epoxide, the process is called epoxidation reaction. The one stored oxygen of that per-acid will just fuse itself between the double bond to form epoxide. If you have this one, by the time you are treating it with peroxyl acid, you discover that it has turned to single bond and the last oxygen has fused itself upon those carbon to form this cyclic ether, which are called oxyrate or epoxide. So conversion of alkene to epoxide is called epoxidation reaction. So let's note that. The class activity 2 before we call it a day. With equation only, show the preparation of per-benzoic acid. Preparation of per-benzoic acid, because of the sake of first class, I'm trying to show it to us. Next subsequent one, you are the one that must be trying it on your own. This is carboxylic acid. If you treat it with hydrogen peroxide, it will fuse one more oxygen on benzoic acid to form per-benzoic acid. So this is CO, C double bond O, that's the first oxygen. Then you will now have the second and the third oxygen. This is the simple equation. Write what are the product of reaction of pent2 with ozone followed by zinc in acetic acid. They are just trying to ask you the ozonolysis of pent2. Pent2 means your in is on position 2. So if you have carbon 1 and you have carbon 2 going to 3, so carbon 4 and 5 is like this, C2H5. So this is pent2. If you treat pent2 with ozone, it's going to give you an ozonide, which when you treat with zinc acetic acid, it will break into two carbonyl compound. So you just have this product. The first product will just be the same place where you remove oxygen. The same place you just fix the oxygen. This one will just be C double bond O plus. If you look at the other one here, you have double bond that you've broken, C linked to C2H5. So all you need to just do is to just break that double bond and fuse the oxygen into it. You'll find the mixture. You can see. So the product of pent2 with ozone followed by zinc in acetic acid is calling us for complete ozonolysis. It will give us this compound, which is ethanol, plus this compound, which is propanol. List 3 examples of oxidizing agent. That's not difficult anymore. We have chromic acid, we have pyridinium fluorochromate, we have osmium tetroxide, we have alkaline or acidified potassium permanganate, and we have ozone. There are so many other oxidizing agents, but we just limited ourselves to these 5 for the scope of this class. For the scope of this class and the content therein. So today we have looked at other things that have, for example, the other ones is the alkene to epoxide, which I've already explained. You can see when alkene is being treated, alkene, we have said, in the oxidation process can be converted to oxyrane, I've shown us, or can be converted to a diol, and it can be converted to mixture of aldehydes and ketone. What caused this third one to happen? The oxidation agent we are using there is ozone in the presence of zinc and acetic acid. That's what is called ozonolysis. And this one, if it is giving us a syn diol, of course, we are using either osmium tetroxide or potassium permanganate. But with osmium tetroxide, will give us a higher yield of diol, but it is toxic and therefore is not environmentally friendly for the health of the user. But if you are using potassium permanganate, it's going to give a lower yield than the osmium tetroxide, but it's safer to use. And this first one to form the epoxide from alkene, it will mean the reaction with peroxide acid. But all of them as they are all oxidation process and they are all oxidizing agents. So you have seen clearly here that various oxidizing agents will be determining factor for the product that you're going to get out of a starting material. As you have seen here in this starting material, we have alkene, but treating it with peroxyl acid, the product is epoxide. Treating it with potassium permanganate, the product is syndiol, and treating it with ozone in zinc acetic acid, the product is mixture of carbonate. So it's on that note we are ending the work for today. Please call others to term that the facilitation have started this week. And by God's grace, we must be meeting on this platform every Tuesday from 6 to 7 p.m. The same Zoom link that has been sent to you is what you will be linking up with every time until this facilitation ends. So thank you very much for your apt attention. In conclusion, we have been able to deal with the following. 1, the definition of oxidation in organic chemistry contents. 2, we have been able to carefully recognize the oxidation as related to organic chemistry. 3, we have been able to list some oxidizing agents, which are 5 of them, and their application and their preparation. 4, we have been able to discuss the conversion of a typical starting material, which is carbon-carbon double bond of alkene, to epoxide. And finally, we have been able to describe the functional group transformation through oxidation process. It's on this note we have come to the end of the facilitation for the first class, which is today. So on this note, I say thank you for your rapt attention, for listening. Deeply appreciate it. Please remember to remind others. So we are meeting here next week, Tuesday, by God's grace. But before then, I will have dropped for you the material you have to read ahead of that next week, Tuesday. And I will have also given you the video that you need to watch before Tuesday. So when you have done all this diligence, we may not need to be repeating the class again, but we may just now begin to look at various troubles or problems or challenges that we are encountering, and we can solve them together until everyone is able to have done it by themselves, so that it is student-centered learning that we are using. Thank you very much, and God bless you.